All right, so welcome back, everybody, to my little video here on what we've been doing in class lately. So in my last video, we discussed about how we can express the side of a square as the root of its area, or we could express it as either a decimal or a decimal approximation. So, in just a 2-second summary, if the area of a square was, let's say, the area of a square was like 36 units squared, whatever the unit is, feet or inches or whatever. If it was 36 units squared, then the side of that square, we could say that that side of that square was exactly, we could say that we could express the side of that square as being the root of its area. Like in this example here, since it's 36, we could say that the side of that square is the root of 36, or we could express it as like a decimal approximation. In this example here, we could say, it would be 6.0 because 6 times 6 is 36. So 6 times 6 is 36, and root 36 times root 36 is also 36. So these two numbers right here are perfectly the same. And that's a brief summary from what our last lesson looked like. So today what we're going to be talking about is irrational side lengths, or some of those tilted squares that we talked about in our last video. So let me put up another real friendly square that we can talk about. So let's say, for example, that we could draw another square that had an area of 49 units squared. Well, if the square had an area of 49 units squared, then we can say, well, we could express the side of that square as the root of its area. And in this example here, we could say, since it's 49, then we can say the side of it is the root of 49, which of course is exactly, this decimal of 7. So these guys right here are called perfect squares. And the reason why they're called perfect squares is because the side of it is a perfect integer, like 7. So 7 times 7 is 49, and then 6 times 6 is 36. Well, in our last video, we also showed you that you could draw other squares that did not have perfect side lengths. Like in our video, maybe you recall that we could draw a square of 5, or a square of 2, or a square of 8, or a square of 10, but the side length was not a really friendly number. In fact, if we used our calculators to try to guess what it was, we found out that the number goes on and on forever and ever and ever, like pi. And it's called an irrational number because nothing times itself equals 5, or nothing times itself equals 8 or 10, So even though we can draw a square of 10, nothing times itself is 10, and the best we can do is estimate it. So the heart of this video is about how to estimate the size of the size of this square right here based upon its area. So let's say that we had this other square that we can draw, like 45. Let's say that we could hypothetically draw some kind of a tilted square that had an area of 25 units squared. Well, and then how long is the side? Well, if we were to sort of take this idea, what we had over here, we can say, well, since we know that the side is the root of its area, well, then one way we could express it is we could say, well, I guess it would be the root of 45. So one good way that we could express this is we could say it would be the root of 45. That's one way to express it. Well, what's the decimal approximation? And that was the real heart of Friday's lesson, was how do you find that decimal approximation? Well, let's look at these numbers over here, and let's just think about side length for a little bit. Well, if this side length over here is root 36, and we knew that that was exactly 6, and this side length over here was 49, and we knew that that was exactly 7, well, we could put these numbers on a number line. So let me see if I can copy this here. See if I can, oh, wow, that's a nice deer. That's not quite what I meant, though. How about this? Let me see if I can try that again here. So let's put this guy down over here, like on a number line, right? Let's say that that would be like the number 6. And let's see if I can copy this without having a deer come up on the screen again. Sorry about that. It is hunting season. Perhaps some of you guys noticed. So let's say that this number right here was the number like 6, and this over here was like the number 7, right? And what we established was that this number, root 49, was exactly 7, right? So we could say, well, those two numbers are very compatible. Is not the right number here, but let me see if I can center that a little bit here. There we are. So this number 7 is exactly the same as root 49. So we could take this number root 36, and we could do the same thing. We could put this guy on a number line over here. Let me see if I can center that for us in here. see if it can come up a little better here. So this number 6 is exactly root 36, and the number 7 is exactly root 49. Well, we could take this root 45, and instead of thinking about them in terms of like being integers, we can say, well, how does it work as compared to like these other radicals, right? So where would the number root 45 go? Well, if this is root 36 over here and this is root 49, well, we can just sort of eyeball where we think root 45 ought to be and come up to be pretty close. Like maybe I would say, well, that seems like about where root 45 would go. If this is 36, then this would be root 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. So maybe I'd even move it a little farther over here. So maybe I would say like root 45 goes about right there. So on a number line, we could say, well, where do we imagine that that is, right? Well, if this is 6 and this is 7, well, then this would be like 6.5 or 6.5. So this must be like 6.7 or 6.8, right? So I could say, well, that number must be about 6.8. And that's how we can go about estimating how big the side of the square is. Since the side of the square is root 45, it exists between the side of this, which is root 36, which is exactly 6, and the side of this, which is root 49, which is exactly 7. So root 45 exists between root 36 and root 49. We're estimating how big that number is relative to the perfect squares that it rests between. So say, for example, if we're going to come up with another number, like let's say root 80, and I was going to ask you, well, how big is root 80? Well, we can think about the perfect squares that root 80 rests in between. Well, root 80 is in between root 81, which is like 9, and then root 64, which is 8. So root 80 is like almost root 81. So we can say the value of root 80 is almost 9. So a reasonable estimate of that would be about 8.9 or 8.95 if you really wanted to get specific about that. And that was our learning target on Friday. So in conclusion, we were able to look at a square, and we could draw any square. For example, if I was to move this guy right down in here, see if I can copy this and move it down into here. I guess I can just move this whole thing down in here. We could say, well, what if a square had an area of, let's say, 10? If a square had an area of 10, well, then we can say, well, the side of the square would have to be exactly root 10. And then we could estimate how long it is by putting it between two perfect roots. So root 10 exists between root 9, which is 3, and root 16, which is 4. And since root 10 is far closer to 3 than 4, we would say that root 10 is about 3.1 or 3.2. And that was the heart of Friday's lesson. I hope that helps.